So in this section, we'll talk about the second big abstract data type that you should know about. These are called symbol tables, and they have a couple of other names. In particular, they're called symbol tables, or dictionaries, or maps, or associative arrays, or key value stores. It's all pretty much the same thing. You may know that Python has a built-in type dict. What you write in these curly braces and colons, that's a dictionary. In Python, it's a built-in type, so you can use this very conveniently. In Java, it's not a built-in type, but it's part of the standard library, so you can use it as well without much hassle. And it's an abstraction of what you do in a physical dictionary as a book, hence this question. But we want to be a bit more abstract than that. So if you haven't voted on the question yet, then let's pause this for a second, because that's the important part. A symbol table has the following operation. You can put in a key with a certain value, which means you associate that value with this key. And in a Python dictionary, you can do this like this. You say, this dictionary at the position k should have this value v. But k doesn't need to be a position. It could be a string or an arbitrary object indeed. Another way to say it is you take a key value pair and store that. You can also retrieve the value that you stored with the key earlier. That's the way how you express this in Python. And that just gives you back the last key you inserted. If you call put several times, it just overwrites, like as you would expect to happen in an array. And you can also delete elements, and you can check whether something is contained. But get and put is the most interesting part. Okay. Yeah, I would say this is one of, if not the most fundamental basic building block. That Python has this built-in as a type is a signal for that. And it's very often that by using a map, a dictionary, a symbol table, you can make your code much more readable. And you should basically use these frequently because they are fairly cheap and can be implemented very efficiently. I want to contrast the notion of a symbol table from something that sounds very similar but has a big important distinction. That's mathematical functions. We often write, well, I'm talking about functions, f of x equals, and then some value, these things, right? What do you do in real analysis? They look quite similar in that both associate some value to a given other input. And this part they do have in common. The thing is that mathematical functions should be seen as a static thing. They're not changed. They're immutable, is another way to say this. If you change a function, then you really get back a new function. So you can have separate functions, they differ in some points, but you can't really change a function in the mathematical sense. You can only talk about a different function. Whereas a symbol table is a dynamic mapping. Both the set of keys that have some value attached to it, as well as the values that you do attach, they can change over time. That's why we have this put operation. And so we still talk about the same, the dictionary doesn't change identity. It's the same dictionary we had before, but we change it. That's a fundamental difference between math and data structures and computer science. We deal with things that change over time because this idea of a mathematical function where you change a small thing and you just get a copy that is a new function, we couldn't really implement that efficiently on a computer. We don't want to be forced to implement it like that all the time. So instead, we allow it to change things. So just keep these two things separate. There's some very easy ways how you can build symbol tables. One easy option is to use an unordered linked list or an unordered array. It's easy to put things in. You can just add a new key value entry at the end. But if you want to find something, you have to linearly scan and find the last entry for a given key. So that's OK, but it's not very interesting. Now, we've had this discussion with heaps before, so maybe it helps if we sort things a bit. How about if we sort them, but here the catch is use a linked list so that we can still easily insert things. And remember, if you want to keep a list sorted, you will have to be able to insert in the middle. So this sounds like a linked list is smart for that because we can do this, inserting things in the middle. But it turns out it's actually no good here because we can't really make use of the sortedness if it's a linked list. The best thing we can do with a linked list is just still walk through. There's no way to jump to a certain position. So it seems like sortedness doesn't help us in linked lists, but of course it does help us in general if we use an array instead. And now this is maybe the most basic algorithm that people also use if they operate a physical dictionary where things are sorted. If you have an English dictionary, there's the alphabet, the words are sorted alphabetically, and then you can find a certain word by a smart way to do it would be binary search. So let's briefly see how this works on an example, but I really think you probably have seen this before. In the general case, we always have a range from L to R that we currently look at. So it's an array, and it has a start and end range. Now, we want to find a key 69. So what we do is we compare 69 with this middle point. So M is in the middle of L and R. And we find that here 69 is bigger. What does that mean? Well, the list is sorted, so everything that comes before 63 is even smaller than 63, which was already too small. So all of these guys are not relevant for our search. I can eliminate those from the further discussion. If 69 is in the dictionary, if it is associated with some key, it will be found in the right half. Okay? And so we move L to this point after M. We don't change R, and we update M, and we keep going. So 80 in this case is too big. I should start with the search key. So in this case, we can eliminate that part and continue with these 3 in the middle. That was not what I wanted. Sorry, I jumped to the back. Now I have to flip through all the slides again. All those memories. Okay, there we are again. So we eliminated this right-hand part. So what's remaining is these 3 elements. Well, and we could just keep going, right? So another round eliminates these 2. And then we're left with a single position. In this case, we find that the key we were looking for is the single key at this position, and then we can return whatever was stored at that point. So for a dictionary, you would have a second array. This is the array of keys, and we would have a second array of values, which is not sorted, but which it just means the key that's stored at position 7 has a value in a different array also at position 7. So you can take the same position and get the key out of there. All right? So that was binary search and very quick. But I think that's all we need for here, because I suspect you've seen this before. So the key step here was we cut things in half each time. And so you can show how often do you have to cut n in half before you get down to 1. That's roughly log n. And if you count precisely, you see that log n rounded down plus 1 is the worst case number of comparisons you need. If you're lucky, it's 1 less. Like it's not much of a difference. The crucial thing here was we needed random access. All of binary search relies on the fact that we can jump in the middle and get the middle key, right? Now, if we were to make this a dynamic data structure, suppose we wanted to insert a key 70, then we would find it does belong between position 8 and 9, but it's no good to make the array contain this new element. We would have to copy the second half over or start with a new array or move a lot of elements around. And then we have linear time again in the worst case. So this is not going to work in a dynamic setting. Binary search is just for static arrays.